Good day, students. I welcome you to your favorite YouTube channel, Physics for Everybody. Today, we'll be solving question on the October-November 2024 Cambridge IGCSE Physics 0625, Paper 4, Variant 1. Do not forget that this year, on this new syllabus, the value of acceleration due to gravity is 9.8. Do not use 10 meters per second squared. Without delay, let us start solving the questions. Question number 1. A spring is suspended from a clamp in figure 1.1 shows a pointer attached to the lower end of the spring. A student suspends loads of different weights from the spring and records the reading on the meter ruler. Figure 1.2 is the reading, that is the reading of weight graph that the student obtains. So this is the graph, okay, plotting the reading on the meter ruler against the weight of the load. Okay, let's see the question now. Using figure 1.2, determine the reading on the meter ruler when, number 1, no weight is attached to the spring. Okay, if you look at the diagram, when no weight is attached to the spring, then the reading will be when the weight is 0, whatever reading you have on the meter ruler, that will be the weight when no load is attached. Okay, and here, looking at the graph, the reading when no weight is attached, the reading we have here is 43 centimeters. 43 centimeters. That's what we have here. Okay, this line here, whatever you have here, that's the reading when no load is attached, and that's 43 centimeters. How did you get 43? Between 40 and 50, we have 5 divisions. Okay, that simply means each division is 2 units. So if this is 40, here we have 42, and then between those two will be 43. Okay, so that's it, 43 centimeters. The next question says, when a weight of 5.6 Newton is attached to the spring. So you come to the weight axis and then you pick 5.6 Newton. Okay, you trace it to the graph, trace it upwards to the slope, and then you trace it to the left to get the reading on length. Okay, you have 63 centimeters here. Okay, so that's why you record here as the reading, 63 centimeters. I've already solved it, okay, to make it faster. Calculate the extension of the spring when the weight attached is 5.6 Newton. Well, when the weight is 5.6 Newton, this was the length, 63 centimeters. And when the weight was 0 Newton, this was the original length. So to calculate the extension, just do the length when the weight is 5.6 Newton. That length of 63 centimeters subtracts the original length, which is the length when no load is attached. Once you take the difference, you get 20 centimeters, and that's the correct answer to that question. The next question now asks us to use the values found in A, calculate the spring constants of the spring. What is the formula for spring constant? K equals to F over E, okay? Force divided by extension. The force is 5.6 Newton, extension is 20 centimeters. Divide the force by the extension, you get 0.28 Newton per centimeter. And that is how you solve this question. Once you do all of that, you are through with that. Now, the C part of the question. An object of mass 0.5 kilogram is attached to the spring. Calculate the weight of the object. What's the formula for weight? Weight is mass times gravity. Good. Weight is mass times gravity. So that's 0.5 kilogram multiplied by 9.8. Do not forget that we said the value of acceleration due to gravity is what? 9.8 meters per second square. Acceleration due to gravity is 9.8. So just multiply the weight by 9.8. You get, multiply the mass by 9.8 rather. You get the weight. Okay, the next question. No, we have not gotten to number 2 yet. The next question now tells us that an object, let me take that here. The next question tells us that the object is pulled downwards until the tension in the spring is 5.6 Newton. The object is released. Calculate the acceleration of the object immediately after it is released. You know, when you pull the spring, Let's go back to the diagram to understand the question better. When a load is attached to the spring, ideally, the spring would extend, okay, when you attach the load of 5.6 Newton. Now, you apply an additional force, okay? Now you apply an additional force. What happened? In that case, that simply means you are pulling the spring further. That means you are pulling the spring further, and this is what you end up having. So that's it. When you pull the spring further, then you've added a force, okay? The additional force in that case is taken as the resultant force. And do not forget that resultant force is mass times acceleration. So the additional force is taken as the resultant force in that case. And the resultant force, which is the additional force you are adding, must be equal to resultant force must be equal to the mass times acceleration. What's the additional force? 6.5 minus what? Minus the weight of the load. What's the weight of the load? 6.5 minus what? What are we subtracting from 6.5 now? So we are subtracting the weight of the load, which is 4.9 Newton. Yes, we got the weight of the load as 4.9 Newton. So you do 6.5 minus 4.9, you get 1.6 Newton. So let me just do that here. 6.5 minus 6.5 minus 4.9, you get 1.6 Newton. Yes, 1.6 Newton. Yeah, and don't forget that resultant force must be equal to the mass multiplied by acceleration. What is the mass? The mass is 0.5. Good. So if 1.6 is equal to 0.5 times acceleration, that simply means acceleration will be 1.6 divided by 0.5, which will give us 3.2 meters per second square. And that is how we got this 3.2 meters per second square as the acceleration of the object. Once that is clearly understood, then we can move to question number 2. Question number 2 talks of a car that is attached to a parachute. Let's see. A drag car is a racing car that is powered by a rocket engine. A drag car accelerates uniformly from rest until it reaches the finishing line. The engine is then switched off and the parachute opens. The car accelerates until it stops. Figure 2.1 shows the drag car decelerating after a race. So this is the graph of the drag car, okay? And we're given the mass of the drag car as 1,400 kilograms. Okay, let's see. The car reaches a maximum speed of 130 meters per second at the time of 6.5 seconds. Calculate the maximum momentum of the car. Maximum momentum of the car is equal to mass multiplied by maximum velocity. And we're given the maximum velocity as 130 meters per second. Maximum velocity is 130 meters per second. So just multiply the mass by the velocity. Mass of 1400 meters per second, 1400 kilogram multiplied by the maximum velocity. Good, and that's what I did here. I multiplied the mass by the maximum velocity. I got 182,000 kilogram meters per second. The next question says, state the feature in figure 2.2 that represents the distance traveled by the car. How would you get distance traveled? Don't forget that this is a velocity time graph. So the area under this graph, this area covered by the graph, represents the total distance covered. That's all. And that's why I wrote here, the area under the graph, okay? The area under the graph line. The next question asks us to do what? Determine the distance traveled by the car in the first 6.5 seconds. And you know, distance traveled is the area under the graph. Good. And what's the area? Look at the shape for 6.5 seconds. What shape do we have here? This is a triangle. Yes, this is a triangle. It forms a triangle, a right angle triangle. So we use formula for area of a right angle triangle, which is half base times height. So in the solution I did here, I use formula for area of a triangle, half base times height. or you do have VT, the same thing. So half the base is the time, which is 6.5 seconds, multiplied by the height is the velocity, you get this. And you can state your answer to two significant figures. Why am I stating my answer to two significant figures? Because the highest number of significant figures I have in the question is two significant figures. Two significant figures. So I can state my answer to two significant figures. The next question says, the parachute opens at 6.5 seconds and the car decelerates. Describe how figure 2.2 shows that after 6.5 seconds the car decelerates. How does the graph show that the car decelerates? Okay, if you look at the graph, after 6.5 seconds, what's the shape of the slope? We have this curve, okay, to the right. And this kind of curve shows you decreasing, it shows you deceleration, okay? It shows that a body decelerates until the velocity of the object becomes 0. Yes, so that's it. That negative slope shows deceleration. So that's it. The steepness of the slope is negative, okay? Yeah, the steepness of the slope is negative after 6.5 seconds. Okay, the question says the deceleration of the car is not constant. How does the graph show that the deceleration of the car is not constant? Well, if you look at the graph, you see that we don't have a straight line. If we had a straight line, then we know that deceleration of the car is constant. Okay? The straight line shows that deceleration is constant. But because the line is curved, that shows that deceleration of the car is not constant. And that's what we have here. The line is not straight after 6.5 seconds. That is, but it is curved. Okay, yeah, but it is curved towards 0. But it is curved. That's it. Okay, now describe the energy transfer that takes place in the car as shown below. What energy transfer is taking place in the car? You know, the energy possessed by the car is kinetic energy. And as the car moves, the kinetic energy gradually decreases to 0. Okay, kinetic energy will be 0 when the car stops. So what is happening to that kinetic energy? It is being converted to thermal energy or heat energy. Yes, it is being converted to thermal energy. That is energy conversion that takes place in a situation like this. So that's why I put in writing here. Kinetic energy of the car is converted to thermal energy by drag force. So it is the drag force that does that job. Okay? So energy transfer from kinetic energy store to thermal energy store. That's it. That brings us to the end of number 2. Now we move to question number 3. Please, if you don't understand this number 2 clearly, just watch this part of the video again. Define moments of a force and describe its effects. And describe the effect it measures. Moment is a product of a force and its perpendicular distance from a pivot, okay, or a fixed point. And what does it measure? It measures the turning effect of a force. The next question. A large rectangular block of stone has a square base of side 3.4 meters. Okay, the length of this side is 3.4 meters because 3.1 shows the block at rest on a horizontal surface. The block is of uniform density and the center of gravity G is at the center. The center of gravity is here. Explain what is meant by center of gravity. It is the point where the weight of an object is concentrated, okay, or where the mass of an object is concentrated. The points where the weight of an object appears to act. Those are the definition of center of gravity. The weight of the block is 1.8 times 10 to the power 7 Newton. Calculate the moment of the weight of the block about point X. Okay, so if you are taking point X as the pivot and the weight acts along the center of gravity, then the distance between where the weight acts and the pivot will be this distance here. Yes, the distance, that will be the perpendicular distance. Don't forget, if you have a beam and we have a pivot here, and then we apply a force of F here, and the distance between that force and the pivot is given by small letter d. Then the moment of that force will be the force multiplied by the perpendicular distance between the line of action of that force and the pivot. Yeah, so that same concept is applied here. The force is the weight, and the distance from the pivot, this is taken as pivot now. So the distance would be half of 3.4, which is 1.7 meters. So that's what we did here. So you multiply the force by the distance from the pivot, okay? The force is the weight. Good. So multiply these two, you get 2.2 times 10 to the power 7 Newton meter. Moments, the unit of moment is Newton meter. Newton meter, that will be the moment of that force. Small letter m represents meters. Don't forget Newton meters. Okay, the C question, the block shown is in equilibrium. States two different conditions that apply when an object is in equilibrium. When an object is in equilibrium, the resultant force is zero and the resultant moment about any point is zero. Those are the two conditions that are necessary for an object to be in equilibrium. We move to the next question. Question number, what number are we moving to now? Question 4. Describe an experiment to determine the specific heat capacity of aluminium. You may draw a diagram. How do you determine the specific heat capacity of an object? This is what you do. You have an object, okay, be it an aluminum block. You supply heat energy to the aluminum block, and then you measure the change in temperature. So you try to determine the heat energy needed to cause the change in temperature. Another thing you can do is you can also choose to have like a bowl made of aluminum, okay? So this bowl or bucket made of aluminum, you then pour hot water. You can pour hot water so that hot water supplies energy to the aluminum, okay? Good. And then you measure the energy supply to the aluminum. How can you do that? The energy lost by the hot water, okay, heat energy lost by the hot water must be equal to heat energy gained by that aluminum bowl or aluminum cup, whichever one. Energy gained by the aluminum. So this is another thing you can do, okay? Since you are supplying hot water, the hot water will lose energy. The heat energy lost by the hot water must be equal to the heat energy gained by the aluminum, okay? And what's the formula for heat energy lost by water? Mass of water, specific capacity of water, change in temperature of water. What's the formula for heat energy gained by aluminum? Mass of aluminum, specific heat capacity of aluminum, change in temperature of aluminum. So this same concept I explained here, that is what I wrote here. So this is the procedure. This is the procedure you have to follow in order to solve that question. What did I write here? Okay, so let's start with the text, okay? Insert thermometer into aluminum calorimeter and measure the initial temperature. So in explanation, you need a thermometer to measure the initial temperature, okay? You must be able to measure temperature so that you can get this variable, change in theta. You must be able to read the change in temperature. So you need the thermometer to do that, okay? Then you must also know the mass of the aluminum. You must know the mass of the water, specific capacity of water. Then you need a thermometer to check the change in temperature. Okay, so when you pour the water inside the calorimeter, you must be able to read the change in temperature that takes place during the procedure. Okay, so if you look at this now, it will make more sense to you now. Look at this now, okay? So insert thermometer into aluminum calorimeter, measure the initial temperature, then pour. I stated the mass clearly, okay? Mass of water you are pouring, and the temperature, initial temperature of the water. Pour it into the calorimeter, okay? Then measure the final steady temperature of the mixture after 30 seconds. Since aluminum is an excellent conductor of heat, it should have received all the heat energy it needs to receive within 30 seconds. So both aluminum calorimeter and the water would attain a steady final temperature. So what you do is just calculate change in temperature of both water and calorimeter, and then you come and use this formula for your calculation. Heat lost by warm water must be equal to heat gained by aluminum. And this is the formula for heat lost by water. Don't forget, quantity of heat energy, quantity of energy equals to MC change in theta for water, okay? Yeah, and so heat lost by water must be equal to heat gained by aluminum calorimeter. And we want to make the specific capacity of aluminum the subject. What will it become? just bring this other two to the other side of the equation, and they become the denominator. And here I have defined the variables. So once you write this like this, you get the answer perfectly. Now the next one, aluminium. An aluminum dish is initially at room temperature. Boiling water is poured into aluminum dish as shown. When you pour water into aluminum dish, what happens? Let's see. Explain why after some time, the dish and the water are the same temperature. Why? Because when you pour hot water inside this dish, the hot water will be losing heat energy, while the dish itself will be gaining heat energy. So heat lost by the water is equal to heat gained by the dish. Fine. But after some time, both the water and the dish will be at the same steady final temperature. So that's what I've written here, okay? Since water is at higher temperature than aluminum dish, heat is transferred from the water to the aluminum dish. And what's the consequence of that? The temperature of the water begins to decrease, okay, since it's the one losing heat energy. While temperature of the aluminum dish begins to increase, and it keeps increasing since it's the one gaining heat energy. And this continues until the water and the aluminum dish are at the same temperature, okay? Or you say until there's no temperature difference between the water and the aluminum dish. That's the procedure. That's what happens. Once there's no temperature difference, then both of them will be at the same, but then heat energy stops flowing from water to the aluminum dish because they are at the same steady final temperature. Good. So, and that's the same concept you apply when performing the experiment used to determine the specific heat capacity of aluminum. We go straight to the next question. Explain in terms of particles why aluminum expands as the boiling water is poured into it. Why would aluminum expand? Because the kinetic energy of the particles of aluminum increases as they gain more heat. And once kinetic energy is increasing, what happens? The particles vibrate faster. And if the particles are vibrating faster, the distance between particles increases. That increase in distance between the particles is observed as expansion. Let's assume these were the particles of aluminum when the temperature was low, and when you increase the temperature, the particles vibrate faster. Distance between the particles increases. So what would you see here? You see it as expansion, okay? But in terms of particles, what is happening is that the distance between the particles is actually increasing. The last question here says, the water in the dish evaporates. Explain in terms of water molecules what is meant by evaporation. What happens during evaporation? The energetic particles that are at the surface of the water, what happens? They escape from the force of attraction between water molecules. Once those energetic particles have escaped, what happens? The less energetic particles will be left in the liquid state. Yeah, and that is what causes the decrease in temperature. The energetic particles break off from the force of attraction between water molecules and escape, and they become gas molecules. So don't forget that if you have a 2 marks question, then you must give 2 valid points, okay? Once you give 2 valid points successfully, then you get your full mark. That's why I made sure I gave 2 valid points to this answer. We move to the next question, question 5. Let's pick question 5 from here. A loudspeaker produces a sound wave in air. The distance between the center of compression and the center of neighboring rarefaction is 0.1 meter. Don't forget that sound wave being a longitudinal wave, it has regions of compression and regions of rarefaction. So that same concept will be applied in what we're doing here. So if you look at what I'm doing here now, you see this region here is a compression. The second one here is a compression, but between them, we have the rarefaction. If distance between compression and rarefaction is 0.1 meter, then you know the wavelength will be double of that because wavelength is distance between compression and rarefaction. 2 times 0.1, that will give you 0.2 meters. Yeah, so that's how I got this correctly. Wavelength is 2 times distance between compression and rarefaction. State the typical value of speed of light. Speed of light at 0 degrees Celsius is around 330 meters per second. And at room temperature, speed of sound, not light, rather, sound. At room temperature, speed of sound is around 340 meters per second. So any value you state within Any value you state within 330 to 340 for speed of sound is acceptable. The next question, calculate the frequency of sound from the loudspeaker. And you know from the formula, V equals to F lambda. That simply means frequency is V over lambda, velocity over wavelength. And that's what I did here. I divided the velocity by the wavelength. Good. So velocity divided by wavelength, that gives me the frequency. The last one, explain whether the sound from the loudspeaker is audible to a human with normal hearing. Yes, 1700 hertz is audible because human can hear 20 hertz to 20,000 hertz, or you call it 20 kilohertz. Any frequency within this range can be heard by human. Frequency outside this range cannot be heard by human with normal hearing. Okay, the next question. Another loudspeaker produces a sound of wavelength 0.4 meters. Sound from the loudspeaker reaches a sound-absorbing surface with a gap width of 0.8 meters at the center. Figure 5.1 shows the arrangement. So this is the arrangement. Explain whether it is possible to detect sound from the loudspeaker at either point J or at point K. Okay, so you know the wavelength of the sound is 0.2 meters, right? So when the width of this no, the one we are dealing with now is 0.4 meters. So wavelength is 0.4 meters, right? So when the width of this gap is 0.8 meters, okay, when the width of this gap, you know, 0.8 meters is bigger than the wavelength. So that simply means there will be no diffraction. But in reality, the wave will not just be straight lines. No, the wave will be slightly curved at the edges. Why? Because the wave will be slightly curved at the, no, straight lines. The wave will be slightly curved at the edges because of what? Because of the sharp edges. As long as there are sharp edges, there will definitely be diffraction, okay? Then if the distance is small, then diffraction becomes more evident. You start having those curved lines, okay? But as long as that distance does not exist, as long as that distance is not very small, then the wave will come out undiffracted, but slightly curved at the edges. So that's what you have. Now they're asking you to explain whether it is possible to detect sound from the loudspeaker at either point J or at point K. At point J, you wouldn't hear it at all, but at point K, you hear it because of that slight curvature of the sound waves, okay? The sound waves are slightly diffracted, okay, but not completely diffracted because the width of the opening is bigger than the wavelength of the wave. So that's what you have here. Explain whether it is possible to detect sound from the loudspeaker at either point J or K. It is possible to hear the sound at J. Good, because sound waves are not completely completely diffracted. It is impossible rather to hear it at J. At J, it is completely impossible to hear the sound wave because the sound waves are not completely diffracted. But at K, it is possible because the sound waves are partially, slightly diffracted. Okay, the waves are slightly curved. The sound wave experiences slight diffraction as a result of the sharp edges. That's all. Once you do that, you've gotten the answer correctly. We move to question number 6. Potential divider is made by connecting a light detecting, a light dependent resistor LDR and a thermistor in series. Figure 6.1 shows potential divider, a voltmeter, and a direct current DC power supply. Okay, direct current power supply in the circuit. A voltmeter measures the potential difference across the light dependent resistor. So there's a voltmeter here. Define potential difference. Potential difference is work done per unit charge, okay? Or you say energy per unit charge in the circuit. That's all. Work done per unit charge passing through a component in an electric circuit. That's potential difference. Now they said the electromotive force EMF for the supply is E. Describe how the potential difference across the thermistor can be determined using the reading on the voltmeter. You want to determine the potential difference across the thermistor, but we want to use reading on the voltmeter to do that. Don't forget that the EMF for the supply is E. So if you have EMF for the power supply as E And we have the reading on the voltmeter, which is potential difference across the light dependent resistor. So to get the potential difference across the thermistor, just do EMF minus the reading on the voltmeter. That's all. Why? Because the EMF will be equal to the reading on the voltmeter plus voltage across the thermistor. Yeah. So if you want to get the voltage across the thermistor, this is the formula you use. EMF minus the reading on the voltmeter. That's all. The next question. The resistance of the light-dependent resistor decreases and the resistance of the thermistor increases. State what has happened to the light intensity. If resistance of LDR is decreasing, it simply means light intensity is what? If the resistance of light-dependent resistor is decreasing, it simply means the intensity of incident light. Hold on, let me check that correctly. Okay, yeah, that's it. It's correct. If the resistance of the light-dependent resistor decreases, it simply means intensity of light is increasing. Why? Because the light-dependent resistor, it has this negative coefficient. What does that mean? That simply means as intensity of light increases, the resistance will be decreasing. Good. So if the resistance is decreasing, then it simply means intensity of light must have increased. And as for the thermistor or temperature dependent resistor, if the resistance, let's see, resistance of the thermistor increases. If temperature is decreasing, then resistance of the light dependent resistor will be increasing. Yeah. So that's it. Temperature of the thermistor must have decreased. Okay, that's the only thing that can cause its resistance to increase. Okay, explain what happens to the reading on the voltmeter when this happens. Okay, what happens to the reading on the voltmeter? Let's see, resistance of the light dependent resistor increases. Resistance of the light dependent resistor decreases. If resistance of the light dependent resistor is decreasing, resistance here is decreasing, then resistance of the thermistor is increasing. What happens? Don't forget that this component of the circuit works as a voltage divider. And voltage divider works based on the ratio R1 over R2 equals to V1 over V2. If we take resistance of the light dependent resistor as R1, and we take resistance of the thermistor as R2, and then we take voltage across the light dependent resistor to be V1, and then we take the voltage across the thermistor to be V2. This formula will always be applied. It will always work. Okay, this formula for the voltage divider formula can always be applied whenever you have two resistors in series. Don't forget that these two are actually resistors. But what kind of resistor is this? This is a light-dependent resistor. It's a resistance is a resistor whose resistance depends on the intensity of light. And the thermistor is a resistor whose resistance depends on temperature. So if the resistance of the light-dependent resistor is decreasing and the resistance of the thermistor is increasing, it simply means the voltage across the light-dependent resistor will be reducing in line with this formula. Yeah, if resistance here is decreasing, it simply means voltage here will also be decreasing. Yeah, and that's the reading on the voltmeter. So reading on voltmeter will decrease. That's just what will happen. So let's see, the reading on the voltmeter decreases, okay, when the LDR and the thermistor are connected in series, they act as a potential divider. Hence, the ratio of the voltage across these two components of the circuit is equal to the ratio of their resistances. And that's what this formula shows. Hence, the EMF of the direct current power supply, since the EMF of the direct current power supply is constant, then this formula can always be applied, okay? Or you state it this way, whichever one you choose, but you state only one formula, not the two of them. So once you do this correctly, then you've gotten the correct answer to question number 5. Question number 6, rather. We move to question number 7. A solid bar is inside a copper solenoid. Figure 7.1 shows that the copper solenoid is connected in series with a battery and a variable resistor. The device shown in figure 7.1 is an electromagnet. Suggest suitable material for the bar. The bar must be soft iron. You cannot use steel because steel gains magnetic properties slowly. But in an electromagnet, you want it to be fast. You want the response to be fast. That means you want it to gain magnetic property quickly. So it is soft iron, or you call it soft iron core, whichever one. No, it is made up of iron, or you call it soft iron. The right hand end of the bar is the south pole. Figure 7.2 shows the bar from above. On figure 7.2, draw at least 6 field lines to show the pattern and direction of magnetic field surrounding the bar. So what would you do here? 6 field lines, we need 6 field, at least. You can choose to draw 8. In my case, I drew 8. So if we choose to just have this diagram, so how I draw my lines of force, I must take into consideration the fact that the left hand side is the north, since the right is the south. And magnetic lines of force come out from the north pole and go towards the south pole. So since the question says I should draw at least 6 lines, I will draw another line and I will draw a third one. But I must take note of something. The distance between the line must be increasing. The farther from the pole, the bigger the distance between the line. And magnetic lines of force do not cross. The lines must not cross, okay? They may eventually meet somewhere because of limitation of space. Here now, they seem to be meeting because of limitation of space. But they must not cross. On no account should you mistakenly draw something like this, okay? You draw a line that crosses another line, okay, or that crosses another line. 2 lines must not cross. You must not make the mistake of producing a line and making it look like this. Once they cross at any point, that point where they cross is considered an error. Magnetic lines of force do not cross each other. The next one, resistance of the variable resistor increases. Explain what happens to the magnetic field surrounding the bar and state the pattern of the field lines. Okay, so if you are increasing the resistance of this wire, then simply means current will decrease. That decrease in current would cause magnetic field to decrease. That's what happens. Current decreases, magnetic field decreases. That's it. The current through the coil decreases, magnetic field decreases. Hence, distance between the lines of force increases, or there will be fewer lines of force. So that's how you answer that question. Distance between the lines increases. What do I mean by that? That simply means that if you were to draw the lines of force in that situation now, your line of force now looks like this. The next line of force can look like this. Yeah. So distance between the lines increases. Why? Because the magnetic field has become weaker. The next question says, a square coil of many turns is placed close to the bar. So now we are introducing a square coil. This square coil was not there before. We are introducing this square coil now. Figure 7.3 shows the plane of the square coil is parallel to the flat circular surface of the right hand end of the bar. Let's see. The resistance of the variable resistor is alternatively increased and decreased. Explain what happens in the wires of the square coil. And when you are increasing and decreasing the resistance, then it simply means current flowing through the coil begins to increase and decreasing. Since the magnitude of current is changing, then it simply means the magnitude of the magnetic field begins to increase and decrease. So that changing magnetic field would cause what? It causes an EMF to be induced across the terminals of the square wire. That's it. It causes an EMF to be induced across the terminals of the square wire. And that is what I've put into writing here. Good. That changing magnetic field, okay, as a result of that changing current, the changing magnetic field that is created causes an EMF to be induced across the terminals of the square coil, okay, across the terminals of the square coil. We take the next question. Now we move to question number 8. The nuclide notation for the radioactive isotope carbon-14 is C14.6. Using the symbols shown in figure 8.1, draw a diagram to show the number of electrons, neutrons, and protons in the neutral atom of carbon-14 and how they are arranged. Okay, so how will you do that? You draw number of, since it's carbon-14, carbon-14 6, it simply means number of protons is 6. You know, atomic number is number of protons. And the number of neutrons will now be 14 minus 6, which gives you 8. So the number of neutrons will be 8. Since number of electrons is equal to number of protons, simply means number of electrons will be 6. So you just ensure you have 6 of the dotted circle. You have 6 of them, 1, 2, 3, 4, 5, 6. Then you have 8 of the hollow circles, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And then electron has 6. That means you have 6 of the star, 1, 2, 3, 4, 5, 6. Don't forget, you should also apply your knowledge of chemistry to this. The first electron shell can take maximum of 2 electrons, okay? The first shell can take maximum of 2 electrons. That's why the first shell has 2 electrons, okay? And then the next shell takes the remaining 4. The next question says, describe how the composition of a neutron of carbon-14 atom is different from the composition of a Describe how the composition of neutral carbon-14 atom is different from the composition of a neutral nitrogen-14 atom. So carbon-14 and nitrogen-14, 7. You know already that carbon-14 has 6 protons, 8 neutrons, 6 electrons. What about nitrogen-14? 7 protons, 7 neutrons, 7 electrons. So it simply means carbon-14 has 1 more neutron. Yeah, carbon-14 has 1 more neutron than nitrogen. You see, when you compare the number of neutrons, carbon-14 has 1 more neutron. Or you say carbon-14 has 1 less proton. Yeah, you know, nitrogen has more proton. Or you even say carbon-14 has 1 less electron. Yeah, since it is neutral, it is not an ion, it is neutral. Then you can also explain it in terms of ions. Okay, yeah. Unless the question does not tell us that it is neutral. When the question does not tell us it is neutral, then you don't have to bring in that concept of electrons. Okay, but if the question stated that they are neutral, then you can solve the question in terms of number of electrons too. Okay, the C part of the question, carbon-14 decays by beta emission. State the name of a particle that is identical to beta particle. That's just an electron. A beta particle is a fast electron. It's an electron moving at a very high speed. It's an electron that is emitted from the nucleus of an atom. Then describe the changes that take place in carbon-14 as beta particle is emitted. For an electron to be emitted, 1 neutron has to change into a proton. Okay, a neutron changes into a proton and emits an electron. That's all. Okay, the D part of the question, number 8 says the half-life of carbon-14 is 5,700 years. A very old object is made of wood. It contains 1.2 times 10 to 11 atoms of carbon-14 when it was manufactured. And then it contains 9.6 times 10 to 11 atoms of carbon-14. When it was manufactured, it contains this. But currently, it contains this value. Now they are asking you to determine the time that has passed. Okay, so the initial number of atoms initial present minus number of atoms presently present. That is 1.2 times 10 to the power 1.2 times 10 to the power minus 11. Sorry. Number of atoms originally present is 9.6. 9.6 times 10 to the power 11. Number of atoms originally present in the beginning, which is 9.6 times 10 to the power 11, divided by number of atoms that are presently present, which is 1.2 times 10 to the power 11. That will give you 8. Yes. So number of atoms that are initially present is 8 times the number of atoms that is presently present. So how many half-life cycles has happened in that case? You know, 1 over 2 times 1 over 2 times 1 over 2 gives you 1 over 8. Or you express this as 2 raised to the power 3. Yeah, that simply means we have 3 half-life cycles. So we have 3 half-life cycles. 3 half-life cycles has happened. Yes, you can try it out. Start with the number of atoms that are originally present and start multiplying by half. Okay, number of atoms that are initially present, start multiplying by half, multiply by half again. By the time you multiply by half the third time, you will get number of atoms that are presently present. That simply tells you that it has gone through 3 half-life cycles. So since we have 3 half-life cycles, just multiply the half-life by 3. You get the time that has passed. And that's what I did here. I multiplied the half-life by 3. I got the time that has passed. 17,100 years, okay? You can write that to 2-second figure as 17,000 years. We take the last question now. Space physics. The Milky Way is the galaxy in which the solar system is located. Still, what is the galaxy? The galaxy is just a collection of billions of stars. Yeah, our Milky Way galaxy is approximated to have around 100 billion stars. Okay, the second question states that the Milky Way has a diameter of approximately 100,000 light years. Determine the distance in kilometer. And you know very well that distance equals to velocity times time. This velocity will be the speed of light, okay, multiplied by time. The time is 100,000 light years. Time must be expressed in seconds, and speed must be expressed in kilometers per second. Yes, so that our distance can be given in kilometers. Speed must be expressed in kilometers per second. You know, speed of light is 3 times 10 to the power 8 meters per second. When you express it in kilometers per second, it becomes 3 times 10 to the power 5 kilometers per second. Okay? Now, we want to express this 100,000 light years in seconds because your time must be expressed in seconds. Express 100,000 light years in seconds. What will it become? It becomes 100,000 light years, right? To change year to day, you multiply by 365. To change day to hour, multiply by 24. To change hour to second, multiply by 3,600. Yes. So you have to do all of that conversion. Okay. So you now do distance is velocity times time, where velocity is speed of light. Speed of light expressed in kilometer per second, which is 3 times 10 to the power 5 kilometers per second. Multiply it by the time in second. Time in second, that's 100,000 times 365 times 24 times 3,600 in seconds. Once you multiply these two, you get 9.5 times 10 to the power 17 kilometers. The next question, astronomers determine the speed and distance from Earth or far galaxy that is moving away from the Earth. State one observation that allows the speed at which a galaxy is moving away to be determined. It's just redshifting. The extent of redshifting tells us how fast a galaxy is moving away. If the extent of redshifting is much, then that galaxy is moving away at a very high speed. It is a receding galaxy. I mean, it is receding with a very high speed, and it has a very wide distance from our Earth. But if the extent of redshifting is little, then the receding speed of that galaxy is small. That's what it shows. Okay, state one different observation that is used to determine the distance of a far galaxy. Apart from using redshifting, we also use the brightness of supernova because all supernovas are considered to be at the same brightness. So if a supernova does not appear very bright, it simply means it is far away from our own galaxy. But if the supernova appears to be very bright, it means, okay, it's not very far away from our own galaxy. States how the speed of galaxies and their distance from the Earth are related. And speed of galaxy is distance from the Earth times Hubble's constant. Speed of galaxy is equal to distance multiplied by Hubble's constant. That's a mathematical relationship. And to get the age of the universe, you take the reciprocal of Hubble's constant. Yeah. So the second question that asks us to determine the age of the universe, estimate. Just do 1 over Hubble's constant. We already have Hubble's constant. Once you take 1 over this value, you get the age of the universe. Thank you for joining us today. If you have any question on this paper, do not forget to reach out to me. Send your questions to my email, physics.4.everybody@gmail.com, and you can reach out to me for personalized tutorial classes. I will teach you online at a subsidized rate. Do have a nice day. I wish you the best of all in your examination. Ensure you visit my YouTube channel for other videos on other examinations. Do not forget to write your name on your exam paper and your examination number. Have a nice day. Goodbye. See you on the next one. Physics for Everybody is the name of this YouTube channel. Goodbye.